If you've been developing software for more than a couple days, then you've definitely heard about protocols. But can you explain quickly and clearly why they exist and how they work? Do we even need protocols in the first place? Hey there, I'm Yakov, and this video is part of the series where I break down the basics of Swift and iOS app development. My goal is to present such topics in a bite-sized and easily digestible way. Because back when I was learning about them myself, that's what always worked best. In the previous episodes, I already had a look at memory management, Swift's type system, and automated testing. Now's the time to explore a new topic, and it is protocols, or interfaces as they're called in some other languages. Just like memory management, protocols are a big and important aspect of software development. And just like with memory management, I'll have more than one video dedicated to protocols. That's because I want to cover them in detail. Today I'll focus on the fundamentals, why protocols exist in the first place, what problem they solve, and what counts as a good protocol. I'd say this video is about the basics of software design in general, so it's gonna be relevant even if you don't work with Swift specifically. Though in that case, I'm really curious how you ended up on this channel. Let me know in the comments. And if you find this video helpful, I'd really appreciate you giving it a like and subscribing. With that said, let's get started. Before we get into the weeds of protocols, I think it's a good idea to look at the big picture. What problem do protocols solve? Are they even necessary? And can we use something we already have instead? These are entirely valid questions, and I don't expect you to believe that protocols are important just because someone tells you so. Instead, I'll try to give a convincing explanation, and please feel free to leave a comment if something remains unclear. I'll start with a real-world illustration. Imagine you're living in the late 19th century, and there's this little thing everybody's talking about. It's called electricity, and from what you've seen and heard, this electricity thing does wonders. You being a talented engineer, just a software engineer, you naturally want to join what promises to be a true revolution. By that point, you already have a few inventions you're ready to offer to the public. But there's a problem. As we're still in the early days of electricity, it turns out that not everybody agrees how it should work. In result, cities across the country have different kinds of that electricity. Some use AC while others DC. Frequency and voltage also vary between places. And even the physical plugs don't always fill the sockets. So, what do we get in practice? First of all, you as the inventor have to build separate models for each electrical system in the country. That's time and money, but you decide to invest them anyway. Problem solved, right? Well, not so fast. Turns out, those fancy trains and railroads have opened the wonderful world of travel to our customers. And now they're also inconvenienced by that abundance of standards, because devices bought in one city may not work in others. Another disappointment. So, does this abomination benefit anyone? Like, anyone at all? Maybe the operators of power grids are the ones who gain something here. You may be tempted to think so, but ironically, even they experience losses. That's because their equipment is sorta unique, which means a smaller market, less competition, and higher prices. The obvious stuff. At this point, you realize something has to change. The nation needs a single interface which offers universal compatibility in terms of voltage, frequency, and even physical design. Luckily, you're not the only one who realizes that. And so, welcome the standard power outlet. This outlet has certain physical properties, a specific size, shape, and pin configuration. These properties are set by your country. Also, your country's electrical code dictates what kind of electricity can flow through wires. If you're a device manufacturer, you just have to ensure that your products adhere to the same standards and have compatible physical plugs. And if you're a consumer, you can buy those devices knowing that they will work for sure. So now the problem is truly solved. All thanks to a single standardized interface. In this illustration, there's a single party which sets the standard and many parties who must comply with it. In software, it's exactly like that. Really, there's not much else to protocols, aside from naming maybe. Setting the standard is called declaring a protocol, and complying with it is called conforming to the protocol in some cases and using it in others. Protocols eliminate the need for software components to know about each other's internals, and even existence. All they have to know about is the common protocol definition. Like, one component wants to use certain voltage and frequency, and it counts that another component will conform to the expectations and supply them. This creates countless opportunities for engineers like you, because existing software now can be extended in the ways that their original authors couldn't even imagine. Just like the authors of electricity couldn't imagine that we'd be using it for this, or this, or this. On this note, I think we're clear about what problem protocols solve. So let's now talk about a few important properties of interfaces in software design. I like the electricity analogy. That's because it mimics not only the general idea behind protocols, but also many of its specific principles. For instance, while the government sets the standard, it doesn't actually generate electricity for you. Maybe it doesn't even know how electricity is generated. The government simply makes sure that everyone knows what to expect when they use the grid, on either side of the outlet. And just like that, the protocol author doesn't have to do anything beyond declaring the protocol. But everyone else depends on that protocol from now on. Another principle and another similarity. The protocol must be implemented in full. If you charge customers for electricity but don't actually supply it, one day you'll be accused of fraud. Swift, just as many other programming languages, is even more vigilant. The compiler simply won't build your code, unless it can verify that your components conform to the protocol and implement its requirements. One important thing to know is that you can make your objects conform to a protocol partially. It's either all or nothing. But well-designed protocols don't force you to implement more than you really need to, and later in this video I'll explain what counts as a good protocol. But wait, this analogy goes even deeper. If you do fulfill the responsibilities to generate electricity, that doesn't mean you always follow the standard. Maybe once in a while you supply too much voltage. Someone's phone or laptop may get toast, but the customers will have a hard time proving it was your fault. Unfortunately, here the compiler can't do much either. Your software components may conform to a protocol on paper, but not do what's actually expected of them. On a personal note, I first learned what a faulty protocol implementation is when I was 6 or 7. Of course, back then I didn't know it was called that. So basically, I found some broken Christmas lights in the cupboard, and I upgraded them to plug directly into AC. In other words, I declared that the lights now conform to the protocol, but my implementation was incorrect, or rather lacking. You can imagine what happened next when I tried to plug them in. At least I'm still alive. Well, if these parallels weren't enough for you, here's more. Electrical standards and software interfaces have a few other things in common. Namely, both ensure decoupling, abstraction, and interoperability. Let's have a closer look. Okay, decoupling. The government dictates the standard. The provider supplies electricity, and you use it for your needs. Everyone knows their own part, but not much else. You don't care how exactly electricity is generated. The provider doesn't care what devices you plug in and how they work. And the government? Well, the government doesn't care about any of you. And just like that, protocols allow different software components to interact with each other. But those components don't have to know about their internal workings. This limits everyone's concern and responsibility. Abstraction. In this case, it kinda extends the decoupling principle, to a point where you not only don't care how electricity is generated, but you also can find it out even if you wanted to. That's because all the complexities are hidden behind the simple interface of a power outlet. Likewise, the provider can come into your home and see what kind of devices you use. In software, implementation details are also hidden behind the interface. We say they're abstracted away. This is deliberate, and it's important that you don't make any assumptions about how those implementations really work. Because if you do, mistakes will follow. You can trust me on that. Interoperability. This principle means that any object which uses or conforms to a protocol can be swapped for another one, and this will not destabilize the system at large. In many cases, other objects wouldn't even notice the change. That is, of course, if the protocol is implemented correctly. Thanks to interoperability that protocols provide, you can, for instance, replace an Objective-C implementation with one written in Swift. In the power grid analogy, an example of interoperability is when you unplug your phone to plug the computer into the same outlet, or when you switch the electricity provider. In both cases, a concrete component has changed, but the system in general still works. I'm pretty sure I'll revisit all these things in a future video, where I'll be focusing on protocols in Swift specifically. Subscribe to the channel so you don't miss them. Hopefully, at this point you understand what purpose protocols serve and what important properties they have. However, my explanations might be too abstract without specific use cases. And that's why I suggest that we have a look at a real-world scenario. In this scenario, solving a task without protocols would be really tough, if not entirely impossible. In iOS apps, just as in many software products, various lists, collections, and tables are the bread and butter of every developer. And in most cases, these structures are populated dynamically. That means you don't know what goes into each row at the time of development. Luckily, frameworks such as UIKit and SwiftUI take care of most tasks when you work with lists. I'll focus on UIKit because it still dominates the landscape. And I'd say that by this point, UIKit has pretty much nailed the whole process, so rendering, scrolling, and celery use are handled for you automatically. But there's one very important task which the frameworks can't solve without your help. In fact, without your help in this task, every other optimization and automation becomes useless. This task is actually supplying and presenting your data in the list. No matter how smart UIKit is, it doesn't know which data you want to display in each row and how it should be laid out on the screen. That is why when you add a UI table view to your app, it asks you to provide a data source object. When the table view is displayed, it will consult the data source about how many rows there is and what goes into each of them. Well, guess what? UI table view data source is a protocol. The table view doesn't care what object will conform to this protocol and how it will be implemented. As long as this object returns the required data, the table view is fine with whatever. And again, it's your job to make sure the protocol is implemented correctly, because the table view relies on it entirely. For instance, if you tell the table view it should have 10 rows, but provide data for only 5, your app will crash. And the table view is not the one to blame. And now I've got a question for you. If you worked with table views before, you know that we often create custom cells. And while doing so, we subclass the built-in UI table view cell. There's no protocols involved. So, my question is, why do we use subclassing in one case, but protocols in the other? I'll be looking forward to your comments. And in the next video, I'll explore in detail this very topic: composition versus inheritance. Subscribe and stay tuned if you're interested. The final topic for today is what counts as a good protocol. If you've been paying attention when I explained the properties and principles of protocols, then you probably have a fairly good idea of what an ideal protocol looks like. But let's get down to the specifics, and also review a few concrete examples. First of all, a good protocol is clear and unambiguous. When you look at it, you know exactly what it does and why it exists in the first place. Perhaps you even have an idea of how you would implement it. Second, a good protocol should be complete and efficient. When it's conformed to by some component, it achieves all of its goals, but doesn't do anything extra, or what we'd call redundant. Third, a good protocol is robust when it comes to edge cases, unexpected input, or malicious actions. Of course, the protocol is merely an abstraction. The actual handling of all those unforeseen events is the job of the implementation. But still, the protocol's design influences a lot. And finally, a good protocol should be flexible and extensible. Ideally, you design it once, and then it can handle all sorts of situations, even those you don't imagine at the time of development. As you can see, clarity and completeness can sometimes conflict with each other, and so can robustness and extensibility. Designing a good protocol is not a simple task. I've seen not that many protocols that were good in every aspect, and I doubt many of my protocols were perfect either. But as you'll soon see, a protocol which violates one or more of these principles can still gain widespread use. So, to give you an idea, here's two examples of high-level protocols. One is really good, the other is notoriously bad. But both are used by billions of people every day. In fact, you're using them right now to watch this very video. The good protocol is HTTP, the one which powers the web as we know it. It's by no means a short or simple protocol. But conciseness wasn't among the required principles. HTTP is very clear in its purpose and mechanism. This protocol describes a way to exchange and present information using a set of well-defined methods, such as GET or POST. It is complete because it covers various aspects of communication, from simple text retrieval to complex data transfer scenarios. HTTP acknowledges potential failures. It provides a mechanism for error handling using status codes. It also supports caching and security mechanisms such as TLS. All that makes this protocol robust. And finally, HTTP is extensible. It evolved through several versions which added new features. But importantly, it maintained backward compatibility. And now let's have a look at a bad protocol. So bad in fact, that it has a track record of breaking the internet on multiple occasions. This is BGP, or Border Gateway Protocol, and it describes how data travels across the internet. Like, remember that time when Facebook services went down and the employees couldn't even enter office buildings and fix them? Yeah, that was BGP. BGP is a fairly complicated thing, with certain edge cases described ambiguously or in a language that's really hard to understand. At the same time, BGP doesn't forgive mistakes, and multiple outages were the result of misconfiguration. What's worse is that BGP lacks the security mechanism which could prevent bad actors from abusing it. The most common thing is route hijacking, and literally any AS operator can do this. Authoritarian governments love to manipulate BGP, and this often comes with consequences for the internet at large. Like, for instance, they want to block some website, and for that they mess with its traffic routes. But now the whole world thinks that this website is hosted in this country. I'm not making this up, there are dozens of such incidents. And BGP isn't very extensible either. While some improvements have been implemented over time, it's not easy to roll them out everywhere. That's because there's about 1 million implementations, and all of them need to interact somehow. I'm not gonna discuss in detail why BGP is like that. Basically, it's just very old. It was designed back when no one could envision the future scale of the internet. But you can see how a poorly designed protocol can haunt the planet decades later. And at that point, it's time to wrap up this video. Give it a thumbs up if it was helpful for your understanding of protocols and their role in software design. But if something remains unclear, I'm looking forward to your comments. I've got a few more videos about protocols planned for the channel, so if you're interested, don't forget to subscribe. Stay tuned for the next episode, and if it's already out, you should see the link on the screen. Make your protocols fly.